In this lecture, I will share some important points about hysteresis in magnetism. Suppose there is a magnetic material that can be easily magnetized by placing it at some external magnetic field. Suppose H represents the intensity of externally applied magnetic field, and this substance will be magnetized when it is placed in this strong external magnetic field H. If induced magnetic field inside the substance is B, then the relation between induced magnetic field and externally applied magnetic field is called hysteresis. How this B changes with the change in value of H. So this is the point of discussion in this topic of hysteresis in magnetism. The variation of induced magnetic field with change in external magnetic field can be understood with the help of this graph. When external field is 0, induced magnetic field in the material is also 0, and we are here. As we increase the value of external active field H, B also starts increasing, and this change takes place as shown in this part of graph. Up to this point, B goes on increasing with the increase in H. And after this value of H, suppose it is H1, H is increasing but B stops increasing, it gets saturated. Then if I decrease the value of H towards the 0 value, then after this B will also decrease, but graph will not follow the same path. In this increasing side, it was in this direction. When I reverse value of H towards 0, the graph takes this shape. Let me again decrease H below 0. Below 0 means if I make value of H in reverse direction, means H is made negative. Then B starts decreasing, and at a certain position B becomes 0. Means induced magnetic field does not become 0 when H is 0, but it becomes 0 for some value of H in opposite direction. That is called negative external magnetizing field. If I go on increasing in negative side value of H, the graph follows this path. And at this stage, again B stops increasing in opposite direction. So this is the path graph followed by. Now if I go on increasing H towards 0, then graph will take this shape. Again in the forward direction, H is increased, graph takes this shape, and this again becomes constant. So this is the variation of B with H. This variation of B shows that B always lags behind H. Means B is increasing or decreasing not parallel to H, but a little bit it is lagging behind. This lagging behind of induced magnetic field against externally applied magnetizing field is called hysteresis in magnetism, and this graph is called hysteresis loop. Hysteresis loop. And during this process, during this complete cycle, some energy is wasted, energy from external magnetic field, and this wastage of energy is equal to the area enclosed by this hysteresis loop. Now let me introduce two very important properties of magnetic material with the help of this graph. One property is called what is meant by retentivity of magnetic material. As we have seen in this graph, when we decrease the value of H from this position H becomes 0 but B does not become 0. It means some magnetism is left in the material from point O to Q. This amount of magnetic field that is left inside the magnetic material when H is made 0, this is called retentivity of magnetic material. It is also known as residual magnetism. So I can write value of magnetic field equal to O to Q. This portion represents retentivity or residual magnetism of the magnetic material. Second property I want to share is coercivity. What is the meaning of this? Let's again discuss this graph. When I decrease the value of H in opposite direction, that is H is made negative, then at a certain value of H, negative value of H, magnetic field inside the body becomes 0. This negative value of H when induced magnetism becomes 0, this negative value of H is called coercivity. So I can call it that value of H in negative direction, that is equal to O to R. So this is the definition of coercivity of magnetic material, and this is the definition of retentivity or residual magnetism of the material. That's all.